Right, so now that we're done bad-mouthing the people who aren't here, then it's safe to record, I suppose. No, one of the most important, one of the most frequently made mistakes with the find method when you call it is you forget to visit the actual parameters before you pass them, which means that their expressions, they have a type field, and their type field is going to be set to null. And find method uses those type fields, of course. So you have to visit the actual parameters before you call find method. And just like you did in phase 3, you created a all methods sequence of all the methods in the entire hierarchy. I have also created and put in for you a constructors list. So there's both the methods and the constructors list, so that you can use find method for finding constructors as well. Anything else? I think phase 3 grades are up. I'm looking at, or we are looking at the MOS results, and there are a couple of issues. So somebody expect to hear from me over the next couple of days for a little get together of some sort. Right. So we can come back and see if there are any other questions in the end. Let me. I want to show you an example of something here that will motivate why SLR might not be the best parsing method we can come up with. So do you guys remember when we did a recursive descent parsing? We said, hey, if there's an epsilon transition, then just fill up the row with epsilons. So if you don't do any of the other ones, and there is an epsilon transition, then we'll take that sort of in an else at the very bottom. And then that means when we do it in the table, we can just fill up. And then we said, well, maybe we should only do it with the follow sets. And then we sort of stuck to this idea of using follow sets for reductions in SL, although reductions don't have anything to do necessarily with epsilon transitions. But look at this here. So look at this partial. Of this partial automaton. We have a state. So we put it here, in which, let me just get my paper. I just wrote this down because I just came up with it. In which I have a state, I have an item that looks like this. And let's say that there's a production, and let's just make it easy. Say that B goes to X. So that means when I apply the closure operation, I get this. Now, that of course doesn't come as a surprise, right? Now let me make another one. Call it C goes to something dot B, little b gamma. And again, when we apply the closure operation, we get something that looks like this. Now, sometimes the reason that a grammar is not SLR parsable is because we get shift-reduced conflicts. And we already saw that one of the ways we could sort of get rid of shift-reduced conflicts was by just ignoring the reduce. But what we could try to do, and which is what we're going to try to work at here, is see if we can find a way to, I was going to say reduce the reduced set, but to reduce on a smaller set. Because what happens with this graph here? Well, we know for a fact that we're going to shift over here on an X. And then we get to this state. We'll call that one it doesn't matter what the other states are called because I don't need to refer to them. But in here, I get that. and I get something that looks like that as well. Now, if I have an input that looks like something, 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 x, b, something, something, something. And actually, let me give these numbers ij and ik. So if we are oops, if we're in I sub j and we see this x here, what do? Well, then we transition and shift to I. What do we do then? Then we reduce by b goes to x and return to ij. So now, of course, out of here, there's going to be a state we can get to. That's going to say a goes to alpha b dot a beta. What's going to happen when I get to that state? Well, now we're going to have a problem because now I've eaten this off the input, right? All this is gone. That's a B. But that's an A. Why did I end up in this state here? I don't know what you would call it, IM. Well, I ended up there because down in this one here, we did a reduction by B goes to X for all Y in follow of B, which is AB. So does anybody see any issues with the way that this is working right now? Doesn't it seem a little strange that when I get down here, I say, right, I will allow that reduction if the next thing on the input is in the follow set of B. Of course, the reason we did that to begin with was to say, well, I should only reduce if that gets me into a state that is possible, one that could exist. And if you see something on the input that is not in the follow set, then it definitely wouldn't give you a sentential form representing a state that would have been achievable. But what we did, we just said, hey, go grab everything that's in the follow set. And of course, we figure that out by saying, oh, you know, somewhere there's this production and somewhere there's this production and there's a B there that has an A there and there's a B there that has a B there. So that follow set becomes A and B. But if you think about it, when that dot moves over here, what do I expect to see on the input? So in other words, what's the next thing that I should see on the input? Well, that's an A, isn't it? Yeah, that's an A. So for this to work, if I'm traveling down this road, I should really only do this reduction with that A. Similarly, if I'm traveling down this road and I end up over here, well, I know that there's a B there, so I should really only do a reduction here if I'm coming from over here with a B. Now, it is true that this A is in the follow set of B because that's how the follow set is computed. And it is also true that that B is in the follow set of capital B because, again, that's how it's computed, right? But I might want to do something slightly different with this reduction. So instead of saying, I'm going to do this follow set business, I'm going to use the context of where this originated to figure out what I should reduce by there. So you can sort of think of this saying, I'm going to annotate this one here, and I'm going to say, when complete, only reduce on A. Actually, it really is the first of that, because it doesn't have to be an A. It could be anything. I just made it an A here to make it easy. And similarly here, when complete, only reduce on B. That one. And of course that one is going to be first of B gamma. So what we're going to do is, instead of writing this little subscript thing here, we're going to introduce something called an LR1 item. What goes here is a regular LR0 item. And what goes here is reduction look-aheads, which is exactly just that and that. And we know how to compute those, because it's just, how do I figure out what the reduction look-ahead of this is? Well, it's just the first set of this thing following that. What's the reduction look-ahead for this guy? Well, it's just the first set of this thing following that. It's not entirely true. There's just one little snag about that, because what happens if that could be epsilon? Then we'd get an epsilon in the first set, and we can never see an epsilon on the input. So what we're going to do is we're going to glue the reduction look-ahead that lives on that one as well. Right. So let's just do a quick example here. So for a production alpha, beta, delta, with a follow set of A being ABC, there exists how many different LR1 items? Well, I need an LR0 item. How many of those can I make? 1, 2, 3, 4, and then I can give them one of those look-aheads. So there exists 4 times 3, which is 12 LR1 items. And they are: A goes to alpha, beta, delta, comma, something. And then let's see if I can copy this a number of times. This is a nice thing about iPadding rather than writing on the board. And then there's that trick with where you can copy that. There we go. Right, let me just change that to a different color so you can better see. So we'll say there, 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 A, 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 there, 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 B, 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 there, 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 and there, C, 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 C. Right, so easy enough. This part is called the core, and this part was the reduction look ahead. Right, so easy enough. Now, we're going to have to figure out what to do with the closure operation. Because what happens when I compute closure? So if we look over here, we said that when I compute closure, so when I add this guy, then the reduction look ahead should be that A. So there's got to be some changes to the closure operation as to how we compute this new reduction look ahead. But that's easy enough because it's just the first set of this plus whatever reduction look ahead we have there. So we can do that without really thinking too much. So new closure operation for LR1 items. Right. So let's say that, and actually, let's just see. We call that closure 1. So let I be an LR1 item. The closure of I is the minimal. That's not how you spell minimal. Set J. So this reads all the same as it did for the other closure. Such that following rule no longer applies. Right, it says if we have something that looks like a dot in front of a B and a reduction look ahead of little a in J, then do the following. If B goes to gamma, is a production of G, then add B goes to dot gamma, comma little b to J, where little b is in the first set. And what we said, it was the first set of whatever is to the other side of beta, and we're going to grab that one as well, because if this becomes epsilon, now all of a sudden that one comes into play. So we get beta A. If not already there. So it's actually very simple to compute these reduction look aheads, and they only ever change. So I'm going to write this down here in red. The reduction look aheads of an LR1 item never changes. So once it's been put in place, which is where this rule is applied, so where we say, oh, there's a dot in front of a B, so therefore there's a rule like that, and it goes in with a dot all the way to the left. When I compute that B here, by figuring out what that set is, while that dot travels all the way to the end there, this B never changes. Why? Well, because think about what that B represents here. It says, when this item is complete, only reduced by that. So I got to drag the dot all the way to the very end before that comes into play, right? So whatever I put in there when the dot is there, that stays there, and when the dot has traveled all the way to there, I now can use this guy to do the reduction. So that also means that when I fill in my table, where normally we say if I have a completed item in an item set, or in a state of the SLR automata, then instead of saying put in the reductions for every element in the follow set, we're only going to put in the reduction for that reduction look ahead. Okay? So let's try a little example of that. Oh, Mason says generally LR0 versus LR1. LR1 reduces only at look ahead symbols, and LR0 reduces at all items. No, it does not. An LR0, yes, sorry, LR0, yes. So, yes, LR0 just doesn't, because that zero you have in LR0 is a it's a look ahead, right? There's zero look aheads. So what can you do if you end up in that state? Well, you can reduce everywhere. So you reduce for the entire row. That's a good point. Yeah, well done. So what we do for SLR is we say, yeah, we're not going to do that. We're going to do it only for the follow set, because that seems more reasonable. Maybe this is actually what I should have said rather than comparing it to the epsilon transitions and the recursive descent parser. But we get the reductions down to just the follow set, and then we're going to say, well, if indeed that could cause, if it causes, it's fine if it works, right? But if it doesn't work, if I get shift reduced conflicts, then what we can do is we can reduce it even further, because we can add this reduction look ahead so that I only actually reduce based on context. Now, if I just go back to, let's go back and grab this one here actually, because we're just going to put that up here. Oops. Not too small because then I can't read it. And then let's try doing it again. So I have ij, and in ij I have a goes to alpha dot b, b a beta, and then I need a look ahead here. I don't know, what should we call it? Should we call it I don't know, Q? There we go. I don't know what it is because we don't have the entire graph here, but Q will do because we never get to it anyways. So now we got to do a closure. So we get B goes to dot X, comma. Well, this part here is the first of A alpha dot A beta Q. So if that first set contains more than one thing, then you will just add a number of different LR1 items. So you get B goes to X and then a whole bunch of different ones. Or you can sort of write it together in a set. That would be fine as well, but we know what it means. But in reality, you're adding a whole number of different items depending on how many things are in that first set. Oops. Now here, that first set is just an A. Now let's do the other one over here. So that's IK. And there we have C goes to delta dot B, B gamma. I don't know, we're going to give this one something as well. What should we call that? P. Then we get B goes to dot X, and we get a B there. And of course we get a B there because of this. So that's just the first of B gamma T. Right, so there we go. Now what happens? What happens with this state here? Well, it splits in two, because that A is not equal to that B. So I'm going to get a state down here, X. I'm going to call it I sub 1, because we need two of them. And it's going to say B goes to X dot comma A. And it really is only in this state, because it's a complete item, that this A is used for anything. It's actually only used, this is only used for saying that my action table at state I1 on a little a is reduced by E goes to X. Now this guy here, similarly, on an X, will go to I2. And in there, we have B goes to X dot comma B. So there we go. And similarly, action I sub 2 on a B is reduced by B goes to X. So we get these states split, right? Although they have the same cores. The LR0 part is the same, but the reduction look-aheads are different. Now, what does that mean? If you think about the SLR, and let's say state I, so I got something like this, and A, B, reduced by B goes to X, reduced by B, reduced by B goes to X. Whereas in the LR1, I had I1 and I2, and this one said reduce by B goes to X, and this one says reduce by B goes to X. Now, what's the difference? Couldn't I just slap these together? Yes, yes, I could, because this part of the grammar is indeed SLR. But if you think about it, the only right thing to do here is to say, well, if the context says that the next thing on the input after doing the B should be an A, then I should only do that reduction on an A. And if the context says that it's a B, then I should only do that reduction on a B. And it also cuts on the ability or the likelihood of getting shift-reduce conflicts, because what if I'd had something else that went in here on this guy, sorry, on this guy, then I could have gotten a shift-reduce conflict there, whereas now it's free and it's free there. So what we do is we spread our reductions over different states, and we get way less of, well, we get the same number in total, but we get less per row. So the chance of getting a shift-reduce conflict is smaller. And if you look at example, I didn't do this one, but example 433, there's an example of a grammar that is not SLR1, because we end up with a shift-reduce conflict. However, when we do the reduction in there, we end up in a state that represents a tangential form that we couldn't have actually created. So let's just do another example here, just to sort of get a better idea. So let's start with I0, and it looks like A goes to alpha, beta, put the dot all the way there, B, delta, comma, A. Really doesn't matter what I have on the right hand side. I just need one terminal and some stuff. Right, so if we've done an alpha, then we can go down here. I1. A goes to alpha dot B gamma comma A. Here we go. And oops, it's not quite right. I had beta b delta, and then I need to move my dot. All right, so now if I do a beta, I get to I2, and I get A goes to alpha beta dot B gamma. Oh, that was delta, sorry, on an A. So we get to there. Oh no, we don't, because now we can add B, and let's just say that it's gamma 1 dot 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 gamma n. And now the question is, what goes here? So if I were to draw this on an exam and ask you, what would you like me to tell you in order to fill out that missing part? What would you ask for? So what goes there? First of B delta, or first of delta A. So James, you need to move the dot 1 over first, because remember, if I go back to here, by the time I get down there, the dot is all the way here, which means that that right hand side is done, therefore this B is done. So now I should expect to see this on the input. So when I compute that first set there, it's always from the other side of the non-terminal, and then all of this stuff here with the comma rubbed out. So Matthew's right, it's delta A. It's first of, oh wait a minute, first of delta A, yeah. So if I say that the first of delta A is a B, then you'll just plunk a B in there, and off we go. And now remember, that B does not change at all. So when I take gamma 1, not a damn thing happens to it. Dot just travels. B stays the same because it is not used for anything in any of these states. That B does not come into play until I get to a complete state. 2 dot 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 n. We get to this state where it says B goes to gamma 1 dot 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 gamma n dot there, and a B. Now that's a reduction state, so that matters. Up here, I can now move on a B, and I get A goes to alpha beta B dot delta comma A. And similarly, that B doesn't, or that A reduction lookup head A here does not change just because the dot is traveling there. And it is actually of no consequence until we get to this state, which is complete, which is where we use reduction look ahead. So we get something like that. You can see that that A originated there. It stayed the same all the way to there. This B originated here because that's where that production that item was added to the item set because of the closure operation, and stays the same all the way down to here. So Matthew is just he's just half a foot ahead of me here. So he says, so in the start state, do we have an LR1 item with the start symbols production for everything in follow of A? No. So let's think about this. If I have so let me actually say, what about the start symbol? Well, we know it only appears once on the left. Actually, so your question for this follow of A thing here, the only thing I know here is that I know that A is a member of follow of A, but that is very unlikely. So either A is the start symbol, and if A is not the start symbol, then I0 has more items in, right? A0 must have more items in, because how did this non-kernel item get into I0 by itself? The only states that have non-kernel items with dots all the way to the left is the start state. So either there's more stuff up here, or this is indeed the start state. And now the question is if A is the start state, what is the follow of A then? It's just dollar. What do I expect to see on the input after having parsed the program? Dollar, right? So in an LR1 automaton, I1 is, sorry, I0 is defined as the closure, and put the 1 there because it's LR1 items. S goes to whatever, comma, dollar. So yes, I suppose actually. So when you phrase the question, so is the start state? So in the start state, do we have an LR1 item with the start symbols production for everything in the follow of A? Well, yes and no. Yes, because that follow set only ever consists of one thing, namely the dollar. Okay. And no, just because I want to be a little bit careful using the idea that if you have a set, then you have only one item. You don't actually. So if, let's just get to that. So if I don't know, if we have something like A goes to alpha dot B C X comma something, and first of CX is D, E, and F, then what I get in here is I get, oh, and let's say that B goes to gamma as usual. Then I get B goes to dot gamma D. B goes to dot gamma E. And B goes to dot gamma F. So what we can do is we can take these and we can write them in shorthand, just because otherwise these states tend to get large. We can say D, E, F, or what I actually like better, like that. Either way is fine. It's just a shorthand notation that tells us there are really three, one for each of the reduction look-aheads following in that second position. Right? So what we could do is now we could what we could do is we could do the dangling else problem part 3, and it's on there, page 229. I'm not gonna do it, but it just turns out that doesn't work either. So it's not even LR1. So now I think it's about time we just give up on that and call that a day. Now you can probably see that if you take a fairly simple grammar and you make it the LR1 automata, then because of the way that states split like this, then I'm going to end up with a lot of states that have the same LR0 part, the same core. And if you look at this, you might say, well, wait a minute. If I'm coming from up here and I get to this state here and I do a reduction by A, or if I'm coming from up here and I go to this state and I do a reduction by B, then these two states here will never have anything but something here and something here. Well, couldn't I just bring that back to this? So if there are nothing, in these states here that would cause a shift-reduce conflict, then I could reduce this by saying, all right, I'm going to merge this into a state I, where I just have that and that. So basically, just this, right? So if I can find two states that have the same cores, if I disregard these look-aheads, these two have the same LR0 parts. Then if I could slap those together with these look-aheads without causing any conflicts, i.e., no shift-reduce conflicts and no reduce-reduce conflicts, then we can actually make this automata smaller. So I'm going to allow merging states that have the same cores if doing so does not cause any shift-reduce or reduce-reduce conflicts. So for states which are item sets in the LR1 automaton, with similar cores, if merging them does not cause any shift-reduce or reduce-reduce conflicts, do so. So let's take this one here again now. Now it stopped working. Hold on. There we go. So if I have this one, then we can merge I1 and I2 to form I1, I2. Well, some new state or whatever. So what it says, is his voice cutting out? No, I'm just mumbling, I think. I've been accused of a lot, but speaking softly has never been one of them. I don't know. I think it's probably on your end then, Benjamin. Unfortunately. Right. So, doing this for all qualified states will generate the LALR1 graph. So if we create the LR1 graph and then merge states with similar cores, if we don't cause any shift reduce or reduce reduce conflicts, then we've now produced the LALR1 graph. That is what the Java Cup tool that you use for your Espresso project does. It creates the LALR1 graph or parsing table for the grammar. And of course, if you can produce the SLR1, then you, or if you can fill in a parsing table based on an SLR graph, then you can also do it for an LR1 by simply knowing that you shouldn't use the follow set, but you should use the reduction look ahead for the reduction items. And if you can do it for an LR1, then you can also do it for an LALR1 because they are exactly the same rules. What we've done there, we've just massaged the graph and made it smaller by merging things together that didn't cause any conflicts anyway. So the only thing we really get is, you can see from this graph, or from this table here, is that these two sort of collapse into each other, and I end up with one row, just like I had in the SLR table. So it is true to say that if a grammar is SLR1 parsable, then the LALR1 graph and the SLR1 graph will be the same. Or is it? Is that true? Is that statement true? Anybody care to try to give me a good argument for why that's the case? And here we are in a stare-off, although nobody can see anybody. I suppose I could turn the camera on and stare at you. But I need a haircut, so we won't do that. Tumbleweed blows. Well, you know, they're all the rain yesterday, so maybe the tumbleweeds aren't blowing so much, but I can hear the, you know, hold on. I have an app for this. There we go. It's my Cricket app. Anyways, I don't know if you could hear that. I think that came through. So let's see what Matthew says. He says, if it's SLR1 parsable, then there will be no stage to merge. Anyways, oh, but that's not entirely true, because you know, how do you create the LR1 graph? You create the LR1 first, and then you start merging, right? So really what you're saying is, if you create the LR, so let's try this argument, because I think you're just saying it slightly different. I think you know what you want to say, but it comes across just ever so slightly wrong. So what are some of the things we can say here? We can say there are no SLR states with shift reduce or reduce conflicts, right? And in SLR, we reduce using follow sets. In LR and LA. LR we reduce using reduction look-aheads which are all in the follow set. So when merging all states with similar cores, the set of reduction look-aheads is still in the follow of the left-hand side. So it's still at least, it's not bigger than that follow set. At most, it's the same. But there are no SLR states with shift reduce or reduce conflicts, and they are based on the follow sets. So this cannot be a problem, right? So therefore, I can now just take anything that has the same cores and slap them together, and I will never get any shift reduce or reduce conflicts because my reduction items didn't correspond to any shift items in the SLR, and neither will they in the LALR when this is the case. So let me ask you this. For a grammar G, I don't know why we needed that in capitals, we don't. Which one of those is the smallest one? For a general grammar G, context-free grammar G. Yeah, the SLR one is definitely the smallest one, because if we agree that when I create the LR, then I get more states, right? Because I'm splitting these I'm splitting many states on these reduction look-aheads, and then when I do the LALR, then I merge them back together. But I only merge if I don't get shift reduce or reduce conflicts. So the best I can do is, if the grammar is SLR, then that LALR will reduce all the way down to an SLR. So I always get something like the SLR for some grammar G is always less than or equal to the LALR for the same G, which is always less than or equal to the LR for the same grammar G. And that's equal if G is SLR1 parsable. Yeah. So I'm just going to do that, and then I'm going to say here core of an item set is what we get when erasing the reduction look-aheads. So if I'm looking at the core for this guy, that's the core, that's core, 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 core. All right. So let's see. Benjamin says, so if it is SLR1 parsable, LA, LR, and SLR would both be equally the smallest. But otherwise, SLR is smaller than LA, LR, which is smaller than just LR. Yes, that is true. That is very true. Because if it's if a grammar is SLR1 parsable, then you create the LR1 grammar, or the LR1 graph, which is going to be bigger, and then you start merging things together. But you're never going to be stopped from merging, because you're never going to find two states that have the same cores that cause shift reduce or reduce reduce conflicts, because the grammar is SLR1. And therefore there are no shift reduce or reduce reduce conflicts in that graph. And since when you merge these together, you never get a merge set in which the reduction lookaheads make up more than the follow set of the left hand side. That's always smaller than or equal to. And therefore, if there were no reduce reduce conflicts in the SLR, there will not be that in the LA/LR for the same reason, because we're not reducing by more, and most the same. And for the same reason, there won't be any shift reduce conflicts. So let's just take a quick look at that. So this is 412.1, which is avoiding conflicts when merging. So let's see, if I have a state I sub I, and I'm going to throw in there A goes to alpha dot A, and the book says B, but I actually think I want to put an A here as well. I'm just going to make a correction there. Actually, the other way around. Sorry. I'm going to say B here and alpha here, and I get this. Is that a problem? No. It is certainly not a problem, because if I see an A on the input, I reduce by A goes to alpha. If I see a B on the input, I reduce by B goes to beta. So no problemo. So we're going to have another one here. A goes to alpha, reduce on B. B goes to alpha, reduce on A. Any problems here? None whatsoever. And they have similar cores. So what happens when I merge these together? I get A goes to alpha, AB, B goes to alpha, AB. What do we got now? We have a reduce-reduce conflict. So it is certainly possible to have two states with no problems whatsoever, and then when I combine them, we end up with a reduce-reduce conflict. So don't do that. That's what we just say. If we end up with a reduce-reduce conflict, then don't merge them. Leave them separate. Okay. Now, what about a shift reduce conflict? Right. So let's look at a. This is a merged item set. IJ. And let's see if we can create a shift reduce conflict. I think we can. We'll say A goes to alpha dot comma something with an A in, and then we just need to make something that can shift on that A. Oops. Then the look aheads there don't matter. So if I have something like that, then how did that come about? Well, that came about from merging this guy and this guy. Right, all right. If these guys were merged, then this one is II, and this is IJ. They were merged, so they have the same cores. So that means A goes to alpha dot, and B goes to beta dot A gamma. Is part of that one. And also here. I'll finish those off. Now I'm going to ask the question. Where did that A come from? Well, it came from either II, IJ, or both. Well, if it were both, actually, let's look at this one here. If it came from there, and I had it there, then look there, shift reduce conflict. Okay, fine. What if it came from here? Well, there and there, shift reduced conflict. So I don't create shift reduced conflicts by merging. They are already there. So merge only if you don't create reduce conflicts. And I think that is all I want to say about parsing. Just be careful about the use of the word look ahead, because there's look ahead, which is what's next on the input, and then there's reduction look ahead, which is that thing we have here, right? What am I going to reduce on when this item becomes complete, when the dot's there? So 415 is other parsing methods. There's some really cool parsing approaches in there. It took me forever to write this, and it annoys me every time that I don't get a chance to talk about it at all. But unfortunately, such is life. I ended up writing way more pages in this book than we have time to go through. So, end of chapter 4, done and dusted. Chapter 5, we have already talked about. You have already used. Chapter 6 is name resolution. We have already done that as well. So now that's my first volume. Pick up the second one, which is now, for some strange reason, missing its back. Which means that we are on to chapter 7, which is titled Semantic Checking. And I think we shall start with that next time. So I think that's what I want to say for today. So if we can use the rest of the time if there are any questions for the project, or any other questions for that matter. Or we can just sit here and stare at each other. I can play the crickets again if need be. Can I go back to the second slide? I surely can. I assume you mean this one. Yes. Okay. Oh, here we are. Earlier, I believe you said phase 3 grades are up, but did you mean phase 2? I probably did. Yes, phase. No, I. Did I mean phase 2 or did I mean phase 3? What? What does that have to do with? That was new due date of phase 3. Oh yeah. I think they are done marking phase 3. They probably haven't put them up yet. I'll talk to Ben. I don't know. I'll talk to him. Right. So let's see. So Marilyn says, "Oh, she's sure that I got that down thing." Okay. Just remember, they do get uploaded to Canvas as well. And then in phase 4, I think one of the bad tests actually goes through using the referencing set. Yes, and that is true, Dennis. That is completely true. Bad test 3 is a very good test if you are implementing all the operators, like the plus operators that work with strings as well. Well, I know that. Oh, maybe they didn't. Maybe they didn't mark phase 3 yet, but they ran MOS on it and just sent me the MOS results. That's probably exactly what happened instead. We also got to figure out when phase 4. What did we get a? Because Ben asked and I just went, yeah. When was phase 4? Did we agree on a phase 4 due date? November 9. Oh yeah, my birthday. Not that I don't love you, but I can't believe that I have to spend my birthday with you guys. So bad test 3, bad test 3 is bad if you don't implement all that stuff for strings, and I think plus on and all that stuff, plus on strings and plus equal on strings and all that stuff is something I did later on. So originally that thing should not have been there. So move that one to a good test, or delete it, or do whatever you want. But if you implement plus equal or plus on binary expressions on strings, then move it to your good test. As I said, I got some MOS results, and I won't mention any names here, of course. However, let me just see that email from Ben. Here we go. So he flagged phase 3s for 1, 2, 3, 4 different groups. 2 of those groups match each other 50%. One of the group matches my solution 45%. One matches the solution 29%, and another one matches the solution 32%. So if anybody might have done something that they shouldn't do, it might be a good idea to get a hold of me before I get a hold of you. Because if I have to go first, it ain't going to be pretty. If you come forward yourself, then I might not get you kicked out of the university. Otherwise, it's not going to be fun. But I will get a hold of the people in question over the next couple of days or so. Now, I don't know where Benny is. I thought he was back from New York, but maybe he got kidnapped or something. Should we offer to pay a ransom if they ask for it, or should we just pretend we didn't hear it? Well, we have a lot of Bens. That's true. We used to have a lot more. At some point, we had like 4 of them. We're down to 2 now. So yeah, if we lose one, then we'll only have 1, and you never know, right? Well, we have another Benjamin in here, and then we have Dennis Benjamin. There's like this is like Benjamins, Bens and Benjamins have turned into what Jasons used to be, or Mikes, right? There used to be like 8,000 of them, and then the Matthews as well, right? There's a well, there's a lot of that too as well. And there's a Mike checking in, so we're everybody's there, right? Just sort of looking. Two Daniels present, just one Brandon. Normally we have a few of those, and one Andrew. Oh, there's another Jan. That's my real first name, which everybody thinks is a girl's name, and it might be for our Jan here. I don't know. Oh, three Matthews spelled in different ways. Two Ryans. Oh, so you're suffering. You're suffering. So Jan Romero's suffering with me, thinking that it's a girl's name, but it really is, right? Well, yeah, I was about to say that, Marion, that that one could be mistaken as well. Two Ryans, one Jacob. Yeah, that's just of the people that are here, right? But anyways, if there are no other questions, then I suppose there's office hours tomorrow, and I guess that's it for now then. So go and do something. See you later. If not tomorrow, then on Thursday. I guess we'll be back, won't we? Yes, we'll be back on Thursday, and hopefully we'll have found that Ben by then. So bye now.